In this section, we're going to look at another consequence of the superposition of waves. Remember that whenever two waves are added together, then the resultant wave is the sum of the separate amplitudes. Now, two waves are travelling and they've got the same amplitude and frequency, and they're also in phase. We want to know what the wave that we see on the screen will look like. So if we have a look at this a little more closely, what we can see, because we're looking at a point directly between where the two waves set off from, then they've travelled the same distance. Here, they're in phase. When the waves reach the screen, then they will superpose because they're in phase, and we will get constructive interference. We'll see a bright spot on the screen at that point. Now, that's known as constructive interference. Using the same setup and the same waves, so they start out in phase, we'll look at what happens a little bit further up the screen. So again, they're in phase, they have the same frequency and amplitude. But this time, the blue wave has travelled just a little bit further. That means that there's a path difference. It also means that there's a phase difference. If we look more closely, then we can see that the path difference is half a wavelength. The waves are now out of phase by 180 degrees. So this time when the two waves superpose, they'll cancel each other out and we won't see anything. There'll be a dark spot on the screen. We have destructive interference. We'll look at one more case. Again, the same starting conditions, so the same waves, but this time they've travelled a little bit further. What will we see at the screen a little bit higher up? Let's look a bit closer. Now, the waves have travelled different distances, but the path difference is one complete wavelength. This means that the waves are now in phase again, and so we will get constructive interference. We'll see a bright spot on the screen. And we can also say that the path difference is lambda, one complete wavelength. If we do this for a lot of wave paths, more than just 3, then what we find is when the path difference is a whole number of wavelengths, we get constructive interference. But when the path difference is a half number of wavelengths, then we get destructive interference. What that means in effect is that we get a pattern of dark and light spots on the screen. Okay? In real life, they may be a little bit more blurry than this. Now, this experiment is based on one carried out in the early 1800s by Thomas Young. And it's known as Young's double slits experiment. It's a very important experiment in the history of science because it was one of the pillars that showed that light was a wave. It was one of the pieces of evidence to show light wasn't a photon as it was thought of, but it was a wave. It also provides evidence of superposition of wave leading to interference, and it allows us to calculate the wavelength of light. Now, Thomas Young was hampered by the fact that he needed to produce coherent sources of light. These are light sources that have the same amplitude, frequency, and are in phase. Unfortunately for Young, light from most sources is not coherent, and that's why he chose to use a single slit, double slit combination. This is the complete experiment. We have a single slit, a light bulb, a single slit, the double slits, and then the screen that we're looking at. The first slit, in order to get the coherent wave, the first slit allows a very small part of the wavefront through. You can see here. So we choose a small part of the wavefront. A little further on, this wavefront spreads out and meets the double slit. And again, we have two small holes which allow a little bit of the light to come through, and that diffracts. Each slit acts as if it were a new light source, but they're coherent because they originated from the same small wavefront. This arrangement, although it was the only practical way to produce two coherent light sources, meant that the light that was produced was very faint indeed, because each time we're selecting a very small amount of the available light. which meant that originally this experiment had to be done in a dark room, and what we saw on the screen is very faint. Now, nowadays, we use lasers which produce an intense, coherent beam of light, so when we do the experiment in schools, we don't need to use a single slit because the light that we're using is already coherent. And this is the pattern that you would see from a laser. You can see that there's a central bright spot and a number of interference fringes. We can use Young's experiment to calculate the wavelength of light used. The single slit is used only to produce coherent light, and so it doesn't affect the calculations. And of course, if we're using a laser, we don't need the single slit. We then have the double slit with a slit separation A. We place our screen a distance d away, and when we look on the screen, we see a central bright spot and the fringes are separated, and we describe that using X. All the measurements here are given in meters. It's worth checking the specification for your particular exam board because they might use different letters to represent these quantities. The equation, however, will be the same. Now, this is the equation that we use. Lambda is equal to AX over D. The wavelength is in meters, slit separation, fringe separation, and slit screen distance, as I said, are all in meters. Now, can you predict what will happen in each of the following cases? If we increase the wavelength of light, if we move the slits closer together, in other words, decrease the slit separation, if we move the screen further away from the double slit. What happens to the fringe spacing in each case?